All right, in this lecture we're going to talk about probabilities in tabulated form, because sometimes you can have two events and compute the probability of intersection, complement, probabilities of condition probabilities, and so on. And it's very convenient to, if you can have the probabilities in tabulated form, because then you can really compute them much easier. So I want to give you an example here, a structure of that. So you have the following. So I have this table here. I have event A and B are complementary. C and D are also complementary events, which means this is B is the complement of A, D is the complement of C. And I am given that the probability of A is 0.62, probability of B is 0.38. So this is the margin here. And also the probability of C is 0.4. Probability of D should be 0.6 because they should add up to 1 if they are complementary. And what I have inside here, these are called joint probabilities. That's the probability of A intersection C is 0.1. Probability of B intersection C is 0.3. Probability of A intersection D 0.52, and probability of B intersection D is 0.08. So that's what it is, and that's what the questions here. Using the definitions, find the probability of A, B, all of these, and that's what we want over here. And probably you should pause this video here and see that you can compute all these probabilities, or repeat what I said. Basically write them down and you can check your answers here after that. Okay, thank you. Okay, so coming back, let's see this structure. So because these things can be complicated and hard to remember, I have this one in this structure so you can never forget what's going on. So this is what goes on. This is A events A and B, C and D, and this is what goes on in the margin here is probability of A, probability of B. In this margin here, probability of C, probability of D, and these add up to 1. In here, I have probability of A intersection C. This is probability of A intersection D, and by the law of total probability, these two adds up to this. So these probabilities add up to this one here. And P of B intersection C, this is P of D intersection C, B intersection D, P and D, they go here, and these two add up to this. These two add up to this one, and these two add up to this one. So if I gave you a problem where not all the probabilities are given, I gave you this and this and this, probably you should be able to get all of that, because from this this one, because they add up to 1, and if then you should be able to tell this from this and this, you can tell what this one here and fill out the rest of the table. Even if I gave you less info and told you the probabilities are independent, the events are independent, so because then what does it mean to be independent? That means this number times this would be this. So are events A and C independent? The answer is no, because 0.62 times 0.4 is not 0.10. So that's the probability of the intersection, that's the probability of the marginal. So that's exactly what we had in the relationship that describes independence. Okay, and let me just show you what that remind you of that relationship here. Clear. So if you remember that P of, say, what do we have here? A and C. P of A intersection C should be equal P of A times P of C. Okay, that's what independence means. A and C are independent if the probability of their intersection is probability of A times P of C. If you go back here, probability of A intersection is here, probability of A is here, probability of C is there, right? And so on. So going back, because this exercise goes back up here and asks you to compute P of C given A, because we know this would be the probability of the intersection of A and C over P of A, all given. P of D given A, we know the intersection of D and A. P of C given B, probability of the intersection of C and B over P of B. What's the probability of B complement? Well, B complement is nothing but A in this case, and P of A union B, so that's going to be P of A in this case plus P of B, which is 1. Or what if I asked you what's the probability of A union C? It would be P of A plus P of C minus probability of the intersection. So you have to keep all of these things in mind. Just use the rules and read the probabilities you have from here. So again, I should pause and answer these questions for a minute. When you're done answering them, come back. And now we're gonna, if you remember, we talked about equally likely probabilities, and we said if we have an experiment where all elementary events are equally likely and we want to compute the probability of an event, we count how many points in A and divide by how many points in S. So if I have an experiment which tosses coins, and I want to toss 10 coins, and I want to find out what's the probability of having all heads. So all heads, there would be only one event in my event, but how many points would be in S? And that would be 10 coins, would be 1024, or 2 to the power 10. Let me go back here. So again, if I toss 10 coins, or if I toss one coin, I would have 2 elementary events. If I toss 2 coins, I would have 4. And if I toss 10, it would be 2 to the power 10. This would be 4 is 2 to the power 2. And then I compute that. So let me go here and see, when you count sample points, things grow very fast. So one coin, you have 2, 4, 8, for 4 I get 16, 32, 64. Now if I get 10 coins, I got 1024. 20 coins, I got 1 million something. So if I want to list all the simple events, that's going to be a big hassle. If I have 30 coins, 10 to the power 9, what's that? That's a billion. Yeah, 40 coins, 10 to the power 12, 50, 10 to the power 15, 64, 10 to the power. So I got an estimate here, so about 2 to the power 30, about 1 billion, 2 to the power 40, well, I got 1,000 billion, or 1 trillion here should be. And oops, someone is trying to talk to me on Skype. 1,000 trillion if I get 2 to the power 50. So if I want, the probability of A would be NA over N. So for some applications we need to find N and NA without having to compute the total number of points in S and A respectively. Well, because that would be really too many of them here. And why would say, because tossing a coin and heads and tails is really a model for a lot of problems. Let's imagine you are inspecting items on an assembly line for being defective or non-defective. So you can think about each time you inspect an item, you are basically tossing a coin where heads indicate defective and tails indicate non-defective. So if you are thinking about a problem where on a day you sample 100 items to inspect, and so that's like tossing 100 coins. If you interested in the probability of 5 of the 100 being defective, and you want to look at all the sample points, you cannot possibly do that, list all the simple events. So you have to compute how many, divide, and get that probability more efficiently. And that's the reason for this section, counting. All right. Let's continue counting. There are some principles of counting. The basic principle is called the MN rule. Suppose 2 experiments are to be performed, and if experiment 1 result in any m possible outcomes, and for each one there are n possible outcomes of experiment 2, then together they will have mn possible outcomes. If you toss 2 coins, that means m times n, because each coin has 2 possible outcomes, you get 4. You throw 2 dice, it would be 6 times 6 or 36. And a small community has 10 men, each of whom has 3 sons. If 1 man and 1 son of his sons are to be chosen as father and son of the year, how many different choices are possible? So, like picking a man would be MN rule, M would be 10, and one of his sons, there will be 3 of them, that will be 10 times 3 or 30 possible outcomes. We can generalize that for any number of experiments. I can have 3 experiments, like tossing 3 coins would be 2 times 2 times 2, or 6 times 6 times 6 for 3 dice, and so on. So that's why I have here is a generalization of the principle of counting, and some examples that I hope you will read. So I want to get to another example here. It's called ordered arrangements, which means the number of ways of ordering n distinct objects taken r at a time. And in this case, order is important. And that will be given by this, n factorial over n minus r factorial. Factorial. So what are factorials? Let's see if you remember factorial. Factorials is a way to summarize computations. If I have 1 factorial, that's equal to 1. 2 factorial is by definition 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6, and so on. 4 factorial would be 4 times 3 times 2 times 1, which is 24. And now you're probably asking question, what is 0 factorial? And 0 factorial by convention is 1, right? So keep that in mind, and then we know what factorial is. So if I go to this example here, in how many ways can you arrange letters A, B, and C? So that's 3, and R is 3, so that would be basically 3 factorial, which is 6 arrangements. Now if we have a box contains 10 balls, balls are selected without replacement. That's key here, without replacement, 1 at a time. So you pick the first one, don't put it back, and then pick the second one. In how many different ways can you select 3 balls and pick the third one? Right? So in this case, it's going to be 10 times 9 times 8, which is doing this part of looking at this side of the formula. So 10 for the first ball, 9 choices for the second ball and 8 choices for the third ball. And you can write that using this side of the formula as 10 factorial over 7 factorial. If you simplify that, it's 720. Okay. Now if you want to, if order is not important, then we call them combinations, and combinations by definitions is NR, which is n factorial over n minus r factorial times r factorial, where this represents the number of combinations of n objects taken r at a time with no regard to order. Just want to give you a little bit about different textbooks use different notation. So for we go to represent some notation. Some books use for combinations, we use n. I used nr or nk. Some books use c and r. Some books use the n and the r here, or n here, r there, and different combinations. And the same thing for the permutations, the one we did before. Some books use p and r, so it's and also on calculators. So these are the different notations for this. So combinations. Now a committee of 3 is to be formed from a group of 20 people. How many different committees are possible? And it doesn't matter really which order the 3 are selected. So if that's the case, that would be 23 or 20 factorial over 3 factorial times 17 factorial. Okay? And we can use your calculators for factorials. You can simplify as I did here and compute. It's up to you. But you can see here 20 factorial is 20 times 19 times 18, and then 17 all the way to 1 gives me 17 factorial, cancels with this 17 factorial. And the 3 factorial is 3 times 2 times 1. Simplify, I get 1140. From a group of 7 men and 5 men and 7 women, how many different committees consisting of 2 men and 3 women are possible? So now I have 5 men. I want to form a committee of, I want to pick 2. I have 7 women. I want to pick 3. And I want to use my MN rule, the first one I used, because my first experiment is picking 2 out of the 5 men. My second experiment is picking 3 out of the 7 women. And in total, I have to multiply them together to get 350 possible outcomes. I want you to finish these computations and make sure that you can get that answer right. Random sampling. But by definition, a sample is said to be random, which means represent. That's what the concept of representation is, representing the whole population if it's random. If n elements are selected in such a way that every possible combination of n elements has an equal probability of being selected. So this is what's called simple random sampling. If n is large, we say the sample is an honest representation of the population. Because if my population is finite, say I have n elements in my population and I want to pick a sample of size n, how many possible samples are possible? So that's going to be all the possible combinations and selected out of capital N. For example, if my population is 28 and my sample is 4, that's going to give me 28 choose 8, that's 20,475 different samples possible. Which means, of course, typically your samples are 20 or 30 out of thousands, so that gives you trillions of possibilities. So what does that mean? Like if I want to pick a sample of 4 out of 28, I want to have to get 20,000 475 different pieces of paper, write 4 names on it, each one. Of course, all 4 names will be, in each paper, at least one name will be different from the others, and that gives me that total. And then pick one. Oh, that's big awkward. So instead of doing that, I just write 28 names, put them in a box, pick 4. That's very close to random sampling, basically. Or I can use tables of random numbers. Tables of random numbers are very useful in selecting random sampling, where you I'll let you read that in your textbooks, but basically, or you can generate random numbers using on Excel now or by Minitab. And if the number you select, so you want to pick random numbers from 1 to 28. So you rank your population members from 1 to 28. If it's 1, you pick the first one. If it's 10, you pick the 10th one, and so on. So that's simply how the random number tables work. And I'll let you read this section on modeling uncertainty. These are my reflections on the topic. And the review exercises here are optional because you will have to do the ones in my stat lab. Thank you. Okay.